Hello and good day to Doctor. In this presentation, it will be about Pelton wheel turbines for Group 1, and this is our lab experiment 5. Our group members will be consist of Jidan Anak Jahit, Muhammad Nur Azman bin Muhammad Fuzi, Christensen Senvermare Verus, which is me, Soraya Najiha binti Muhammad Ishak, and Muhammad Arif bin Mustafa. And my ID number would be MA16156. So I will be doing the introduction for chapter 1. So as we all know, energy can exist in many types of forms, and one type of energy is the hydraulic energy, which can be in the form of kinetic, potential, or thermal energy. Now, hydraulic energy is converted into mechanical energy by energy producing machines such as turbines and motor. On the other hand, energy-consuming devices such as fan, pumps, and compressors use mechanical energy from the shaft to generate hydraulic energy. Turbines are machines that extract energy from fluid, and fluid puts torque on the rotor in the direction of motion according to its geometry. There are two types of turbines: impulse and reaction turbines. Our research will focus on the Pelton wheel turbine, a type of impulse turbine. We will also be covering the parameters that influence the performance of the Pelton wheel turbine. So, in this experiment, the problem statement for this experiment is that we want to achieve the highest efficiency rate. In order to achieve this, the Pelton wheel turbines must be selected from a variety of operational parameter ranges, which means we will be using different parameters until we will achieve the highest efficiency rate on the Pelton wheels. The objective of this experiment is to investigate the Pelton wheels turbines constructional details, and the second objective is to see how different parameters affect turbine performance. Like I said before, we will be using different types of parameters in order to find the highest efficiency rate. Next is the project scopes. The goal of this project is to determine whether the project goals are more likely to be met, and the following factors should be considered when carrying out the project. First one is to investigate the parameters that influence the efficiency rate of Pelton wheel turbines. The second one is hydraulics bench is used to observe water flow in Pelton wheel turbines.
So hello everyone, my name is Jidan Jahit and my matrix number is HP17007 from Group 1, Section 1. And for lab number 5, which is the Pelton wheel turbine, I will be explaining about the chapter 2, which is the theory. The first explanation that I'm going to tell you guys is about the turbine. Turbine is about the energy producing devices. They extract energy from the fluid and transfer most of that energy to some form of mechanical energy output, typically in the form of a rotating shaft. And the fluid at the outlet of a turbine suffers an energy loss, typically in the form of a loss of pressure. And there are three types of turbines, which are the steam turbines, gas turbines, and water turbine. And steam turbine is a mechanical device that extracts thermal energy from pressurized steam and transforms it into mechanical work. Gas turbine is a machine that harnesses the energy obtained within gas, either the kinetic energy of motion of flowing gas, steam, or the potential energy of a gas under the pressure to generate rotary motion. And lastly, water turbine is a rotary machine that converts kinetic energy and potential energy of water into mechanical work. And for this experiment, we are going uh, focus more on water turbine, and it is also related to in impulse turbine. Impulse turbine is actually the fluid is sent through a nozzle so that the most of the mechanical energy that available is converted to the kinetic energy, and the high speed jet then impinge on bucket shaped vanes that transfer energy to the turbine as shown in this figure over here. And this first figure over here shows the schematic diagram of a Pelton type impulse turbine. And this explanation actually explains about the history of Pelton wheel. The Pelton wheel is an incentive model steam turbine made by an American designer, which is Lester Allen Pelton in the year of 1870s. And Pelton wheel removes the energy from the pressure of the running steam, essentially exposed to stream inert mass like the old overshoot water wheel. And what we can say about this design is that the Pelton design removed nearly entirely of the water impulse energy, which allowed for a very efficient turbine. And this figure over here shows some of the advantages of using Pelton wheel. The first is the overall efficiency of the turbine is high, and it operates on the high head and low discharge. Each bucket splits the water jet in half, thus balancing on the side load forces or thrust on the wheel and thus the bearings. A Pelton wheel is also very easy to assemble. It is very easy to function, and it operates with a very flat efficiency curve. And lastly, it has a tangential flow, which means that it can have either axial flow or radial flow. And this figure number 3 shows the example of an old Pelton wheel from Walchensee Hydroelectric Power Station. And Pelton wheels are the selected turbine for hydropower wherever the open water source becomes a comparatively large water-powered energy at low current flows. And these are some of the formulas that are being used for this experiment. For the formula of Pelton, the first one is the specific speed, and this is the formula that we are going to use to find the specific speed, which is the frequency of rotation. We multiply it with the square root of power, and then we divide it with the square root of density with the multiplication of gravitational force and water head to the power of 5 over 4. And these are the other common formulas that are being used, which is the potential energy, kinetic energy, initial jet velocity and power, and also turbine efficiency. And lastly, this is the formula for finding the torque of the water turbine. And this first formula shows that the force F exerted on them by the jet runner is equal to, but contrary to the V, to the and the rate of momentum shift of the fluid by Newton's second and third law. Thus, it comes to this formula. And for the second formula, uh, if the D is the wheel diameter and the torque on the runner will be equal to the force divided by the diameter of a 2, and we come up with this formula to find the torque. And that's it for chapter 2. Thank you.
Okay, Assalamualaikum warahmatullahi wabarakatuh. My name is Suraya Najihah binti Muhammad Ishaq, MA 17096. So today I will present chapter 3 for this experiment. The Pelton turbine model is located in the food laboratory. This figure 3 is the schematic of the experiment setup. Okay, so this is the experimental procedure for this experiment. First, close the two drain valves positioned on the releasing basin. Then open the discharge controlling valve on the inlet pipe and record the pressure on the pressure gauge. Next, loosen the torque brake so that there is no friction applied on the turbine shaft. Adjust the torque gauge display to 0 reading. For this setting, the tachometer should read a rotational speed of about 1800 rpm. After the water level in the basin has become steady, measure the head on the weir using the point gauge located on the basin. Then measure the rotational speed of the shaft with no torque resistance on the shaft with the provided tachometer. Carefully align the tachometer reading line perpendicular to the phosphorescent tape on the shaft. Then tighten slightly the friction handwheels and record the torque display on the friction gauge as well as the rotational speed of the shaft with the tachometer. Then repeat this step until approximately 10 different settings are obtained with the last setting with the turbine stopped. Then after the shaft is fully stopped, completely loosen the torque brake and zero the friction gauge. Then increase the discharge by opening the pipe inlet valve to a runway speed of 2000 rpm and repeat step 2 through 7. Then last one, open drain valves and allow the basin to drain until only a trickle of water flow over the weir. Wait for weir flow to stop, then measure the water depth indicated by the point gauge. So that's all for me.
Assalamualaikum. My name is Muhammad Nur Asman bin Muhammad Fuzi, MA14112. I will continue our group presentation on Chapter 4, Result and Discussion. First, for the result, there are two results. First is turbine characteristic curve with constant pressure 0.2 bar and constant flow rate with 30.9 liter per minute, and power curve with constant pressure 0.2 bar and flow rate 80.75 liter per minute. For the turbine characteristic curve, we are going to collect the data for the rotational speed, moment on the shaft, power out, power in, and efficiency. For power curve, we are only going to collect data for rotational speed and power out. For the graph, this is the graph of moment on the shaft versus rotational speed from the data we collect from the experiment. From the graph, you can see that the moment on the shaft increase when the rotational speed RPM decrease. The moment of the shaft decrease when the rotational speed decrease is almost constant value. Next is the graph for the power out versus rotational speed. For this graph, as you can see, power out of the Pelton wheel will increase when the rotational speed increase, but the power output will decrease when rotational speed around 555 rounds per minute will continue to decrease.
Okay, Assalamualaikum warahmatullahi wabarakatuh. Today I'm going to present about result and discussion. Continue for the result of two more result. And first of all, my name is Muhammad Ali Mustafa and MA 17157, and I'm going to present about the Lab 5 result and discussion. And firstly, I'm going to talk about the efficiency of rotational speed of the result. Okay, as you can see, this is the figure 4.2 power out versus rotational speed, and this figure shows that the graph between efficiency and rotational speed. The graph show that the efficiency will be increased when the rotational speed of the increase until 300, 500, and 30 and plus, and then it will decrease. And second is effect of flow rate to the power out. This is the figure 4.4. It's about the power curve. This shown the effect of flow rate of the water jet to the power out of the pattern wheel. And from the graph, we can see the power out of pattern wheel for the flow rate 80.75 liter per minute. Liter per minute is lower compared to the flow rate at 30.9 liter per minute at the rotation speed lower than 500 rpm. However, when the rotational speed exceeds 600 rpm, the power output for the flow rate of 80.75 liter per minute is the highest compared to the 30.9 liter per minute. And for discussion, we can study about the relationship between power and efficiency of pattern turbine at different rotational speed. And we managed to get the data which when the power increase, the efficiency of pattern turbine at different rotational speed also increase. This show that more power is needed in order to get higher efficiency of pattern turbine. And the power is crucial so that the pattern turbine work efficiently. Second is the performance and turbine characteristic was observed, and we managed to determine that when the rotational speed decrease, the moment on the shaft will increase. Therefore, there will slow rotation produce on the work done for the pattern turbine, because when the moment on the shaft increase, the efficiency of the pattern turbine also increase. That's all for me. Thank you.
For Chapter 5, which is the conclusion, we have concluded that the best operating parameter for Pelton wheel turbine is when the rotational speed is at 534 rpm, because it can achieve the greatest moment on shaft, maximum output power of 5.6 watt, and the highest overall efficiency, which is 61%. Thank you.